Good morning, ladies and gentlemen. My name is Harold Ballesteros, and I will be delivering this presentation. In this work is also composed of Professor Noriega Sanchez, who is the main author, Professor Gustavo Guerrero, and we all work at Francisco de Paula Santander University in Ocaña, Colombia, and Professor Rogerio Gomez de Oliveira, who belongs to the University of Santa Catarina in Brazil, who collaborated with us with the preparation of the document as well as the analysis that was presented in it. In this paper, we will present the main ideas of our work that was submitted to this event, which deals with the mathematical model of a reactor for solid chemisorption refrigeration systems. The following will be here in the net. We have the outline of our presentation. First of all, we will discuss the introduction, where we will contextualize the problem to treat. Then we will talk about the method of the mathematical model that was modeled for the reactor and the considerations that led us to that model. Later, we will give the main results and finally the relevant conclusions about the work. As a little bit of an introduction, we can see here the energy consumption from non-renewable energy sources. I believe that for no one is a secret the high dependence of the world on non-renewable energy or fossil fuels. In getting more into context of our work, according to the International Energy Agency, refrigeration systems consume between 10 and 20% of the world's energy. So applications that aim to reduce that consumption or explore new alternatives or systems that produce a cooling effect, reducing energy consumption, are very attractive. Um, so one of the systems that has the purpose of not using electricity but using waste heat instead are the sorption cooling systems. They produce the cooling effect as the steam compression system, but with the difference that they use waste heat or thermal sources. The sorption refrigeration systems are divided into physical adsorption systems and chemical solid chemisorption refrigeration systems. These systems have their advantages and disadvantages. However, our work was particularly based on solid chemisorption systems because these systems exhibit different advantages over adsorption systems. For example, um, they have higher adsorption capacity of the refrigerant by the adsorbent. And the refrigerant that normally use these systems are environmentally friendly because they have low GWP, global warming potential, and zero ODP, or ozone depletion potential. Another advantage is that these systems are less sensitive to shock or movement since they do not have moving parts. However, this system also presents some disadvantages. Mainly these two disadvantages, they are the low coefficient of performance and the cooling power. Several works in the literature have addressed this type of problem, and most focus on the main device of those systems, that is the reactor. Um, the reactor will be the equivalent of the compressor in steam compression systems. Therefore, the best improvement that can be done to this system are those that are done to the reactor. Since this system replaces the mechanical work that makes a compression system. Many of the work of the literature approach the mathematical modeling of this system, applying system in one dimension, and very few approach the two-dimensional system. Therefore, the model that was proposed in the following work has the purpose of predicting the behavior in a sorption system, and on the other hand, to identify alternatives of improvement of that system, since the mathematical model allows to explore how these variables can influence the behavior of the system. Um, from what was consulted in the literature, in figure A here, we observe the reactor of the sorption system that was modeled. Basically, it is a concentric tube heat exchanger. In figure A, we observe the entrance and the exit of the thermal fluid, that is the one that cools or heats the system. In this case, the sorbent bed. In figure B, we have a cutaway view of the reactor. In it, we can see the fins that were modeled, and the one that is inserted into the sorbent bed here. We also observe here the internal tube in which the refrigerant vapor flows, that is absorbed or dissolved from some chemical kinetic condition of the system. So moving on, here we have the mathematical equations that were modeled to represent the heat transfer inside the reactor. The first equation represents the heat diffusion inside the sorbent bed. From left to right, we have this term, which represents the volumetric thermal capacity. This term was calculated taking into account the contributions of expanded graphite from the metallic salt, and by the amount of refrigerant that is absorbed or dissolved during the synthesis and decomposition phases. The expanded graphite appears here since, according to the literature review, the metallic salts used in these systems has a very low thermal conductivity, and therefore the addition of graphite had the purpose of increasing the heat transfer inside the sorbent bed. Lambda here represents the thermal conductivity of the sorbent, since we are talking about a solid porous medium, and the second order derivatives C and R represent the radial and actual heat transfer in cylindrical coordinates. And the last term of the equation, this one here, represents the energy generation of the sorbent bed during the synthesis and decomposition phases. That is to say, the endothermic and exothermic reactions of the system during the two phases. This is the most complex term in the equation, since there is dependence on the dynamics or chemical kinetics of the adsorbent. This can be represented by this equation, the partial of x with respect to t, where AR represents the Arrhenius factor and is associated with the energetic parameters of the absorbent, which also depends on the temperature. X represents the conversion capacity of the system and varies between 0 and 1. P, this term here represents the equilibrium pressure, and this represents the evaporating pressure. A similar equation is placed for the decomposition phase, but instead of having evaporating pressure, we have condensing pressure. The equilibrium pressure is calculated according to this equation, which is a function of certain constants. For example, R represents the universal gas constant, T here represents the temperature, and the other two terms represent the enthalpy and the entropy respectively. Moving on, so the effective thermal conductivity was another variable that was modeled. The truth is that there is no defined model to calculate the effective thermal conductivity of metallic salt for sorption systems due to the difficulty of calculating this parameter in function of chemical reactions. So, from extensive literature review, it was found that the thermal conductivity of metallic salts such as calcium chlorate, manganese chlorate, barium chlorate that use ammonia as refrigerant do not suffer a considerable variation if R maintained the number of moles, the apparent specific gravity, and the graphite fraction in the sorbent bed. Therefore, from that consideration and from experimental values reported for different salts, a linear equation here was adjusted for thermal conductivity, where C1 and C2 are adjustment parameters, which have been determined by minimizing the error of the density calculated as a function of the number of moles and the density calculated experimentally. In relation to the thermal conductivity in actual direction, it was considered a parameter of anisotropy phi here in order to consider the impact of porosity on the sorbent. In this sequence, to solve the adsorbent heat diffusion equation, we have a temporal condition for time equals 0 here, you can see, and where the temperature is ambient temperature. X here represent the conversion rate that at the beginning will be 0. That is to say that at the beginning of the system no refrigerant is absorbed, and in radial conditions we observe that the constant that we consider a constant resistance, and in the actual direction here, it was considered that the adsorbent bed between two fins in which two constant resistance were also considered. One at the beginning, or C equals to 0, and the other one in C equals to lambda. So moving on, in order to understand a little more how these boundary conditions were established, then in this figure we present two reactor views. In the first one, the figure explains the boundary condition in direction R here. So we observe an internal radius of the tube where the refrigerant flow. It was considered that the velocity of the flow is very low and therefore adiabatic. In the detailed view in B here, we observe that two constant resistance were considered between the fins and the sorbent bed. One here and the other one here. So moving on, here we can observe the other models of the heat diffusion in the different components of the heat reactor, such as the tube wall, the fins that are in the sorbent bed here, and the thermal fluid that flows through the annular region, where the second order partial derivatives were numerically discretized from the center finite difference scheme, and the first order terms. For example, in the working fluid, these equations were discretized using a forward discretization system. In this slide, we have the equation that allows determining the performance parameters of the system, especially during the synthesis phase, that is where the absorption state of the refrigerant occurs in the system. The first equation here represents the specific cooling power, that is a measure of the capacity of the cooling power produced as a function of the absorbing mass that we have in the system, and the COP is the coefficient of performance and represents the measure of heat utilization that is being supplied to the system. Q, this term here, represents the heat of the refrigerant that occurs during the synthesis phase, and the other terms, these two, represent the absorbed heat of the sorbent bed, such as the latent heat and the sensible heat. In this part of the result, it was verified the solution convergence of the system of equations, especially those given for the energy generation term for the sorbent bed, where it was found that with a time increase equals to 10 seconds, the system experiences a certain divergence, and therefore there is no effective solution of the whole system of equation. From these results, or from the base case that was considered for this model, it was found that the minimum time to solve the system of equations that were proposed in the present work is 2 seconds and mesh sizes less than 2 millimeters. On the other hand, in order to validate this result, the results obtained from the mathematical model considered were compared to the experimental results. This time we considered the result of Wang and collaborator for the synthesis and the composition phases. And it is observed here, the experimental model validation, that the model has a very good correlation to those results obtained from the experimental validation. One for the composition phase, we can see here, and the other one for the synthesis phase. It was found that the absolute error was less than 6%, and this emphasizes the precision of the model. In this figure are presented the temperature profiles and the absorption rate of the refrigerant by the system. This in order to know a little more of the dynamics of the chemisorption refrigeration system. The first figure, shows the temperature profiles. The continuous line here and here represents the temperature of the thermal fluid flowing through the annular region, which was at 140 degrees Celsius here during the synthesis phase, and 30 degrees Celsius during the decomposition phase. Note that after the Schiff cycle here, this system enters in a periodically developed regime, and therefore the execution of additional cycles become unnecessary. In the same way, the absorption rate here indicates this dynamic, making that from the Schiff cycle the absorption and desorption rate of the refrigerant is stabilized between 0.29 and approximately 0.65. Once the model is properly implemented and validated, the next stage in this results phase is to investigate the impact of operational parameters. The first analysis presented here is this figure for the consolidated sorbent. Note that for consolidated sorbent, the increase of the time of the cycle brings a negative impact on the specific cooling power. This is due to the fact that the conversion rate is not linear, and therefore this is reflected in the decrease of the specific cooling power. However, the coefficient of performance is positively influenced by the time. That is to say, as we observe here, for the specific cooling power, the greater the time, the lower the HCP, as we observe here. Lower time shows a higher specific cooling power. For the COP, we have the opposite. When the time increases, the COP also increases, as we observe in this figure here. The radius also give a very similar impact. In other words, the greater the radius here, the lower the coefficient, the specific cooling power, and the greater the radius on the COP, the greater is the COP, as we observe in this figure. A similar trend is observed for the system, but in this case with sorbent powder, that is, sorbent that is not compacted inside the reactor. In this case, the specific power is slightly higher than the consolidated sorbent, and the COP is slightly lower for the system with sorbent powder. In other words, despite the fact that the consolidated sorbent has a higher conductivity value, there are still considerable temperature gradients that reduce this thermal power inside the system. So, from the results of the implemented model, we obtain the following conclusions for the present work. The proposed mathematical model allows simulating satisfactorily the operation of a reactor to solid chemisorption refrigeration systems. The cycle time and the reactor radius influence the HCP and the COP in the opposite way. Internal temperature gradients in the powder absorbent are higher when compared to consolidated sorbent. To assess the impact of a larger number of geometric and operational variables on the HCP and the COP through multi-objective optimization. So, on behalf of the other authors, we thank you for your attention, and it has been a great honor to participate in this conference. Thank you very much.